channel Knowledge Hub and subscribe to our channel and click the bell icon for the latest update. Today we're going to start with your physics class 11th class, that is your class 41th class of the session. Now in this physics class unit 5 we have to start with the laws of motion. That is what we have to discuss here. So in laws of motion we had done last topic we had done is the equilibrium of a particle. Today we'll do the numerical for that. In the last class we have done f1x plus f2x plus f3x equals to 0, f1y plus f2y and plus f3y equals to 0, and f1z plus f2z and plus f3z is equals to 0, where f1x, f1y and f1z are the components of f1 along x, y, z direction respectively. We'll start discussing about the question here. It is the sixth question of this unit. Although the question here, before starting with the same, it's a huge request to all the viewers to please go ahead with like, share and subscribe so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Question is, a mass of 6 kg is suspended by a rope of length 2 meter and from the ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope, and what is the angle the rope makes with the vertical in equilibrium? Take G equals to 10 meters second square and neglect the mass of the rope here. So let's go for it and we'll be figure it out. So a mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope what is the angle the rope makes with the vertical in equilibrium? Take G equals to 10 meters second inverse square, neglect the mass of the rope. So let's go for it. We have a figure here. This is 50 Newton. angle making is theta. This is 1 meter. This is your 60 Newton. This is your weight, 1 meter B. This is D1. Now this is the figure 1A. The B figure is 60 Newton. This is the weight, D2. And this is the B figure. C figure we have 50 Newton. This is the angle theta. D1. This is D2. Okay, this is the figure C. Now we go for the solution here that we'll be solving, where you have to remember in my equilibrium of a body that requires not only translational equilibrium, which is zero net external force, but also rotational equilibrium, zero net external torque, as well as that we'll discuss in the next coming classes, next coming unit as well in a detail. So for that we'll be going for the solution here, and let's go for the same. So the solution, so for that question here, you have to, in figure B, if you see and see, that are known as a free body diagram, and the B is the free body diagram of W, and is the free diagram of point P. Consider the equilibrium of the weight W. Consider the equilibrium of the weight W. Clearly T2 equals to 6 into 10, which is equals to 60 Newton. Consider the equilibrium of the point P under the action of three forces, the tension T1 and T2, and the horizontal force 50 Newton. So the horizontal and the vertical component of the result force must vanish separately. T1 cos theta equals to T2 60 Newton. T1 sin theta equals to 50 Newton, which gives that tan theta equals to 5 by 6, or theta equals to tan inverse 5 by 6, which is equals to 40 degree. Note that the answer does not depend on the length of the rope assumed massless, nor on the point at which the horizontal force is applied. So now we go for another one, which is the another topic, that is the common forces in mechanics. So that we go for it. We deal that. Common forces in mechanics. And common forces in mechanics here that we discussed. In mechanics, we encounter the several kinds of forces. The gravitational force is of course pervasive. Every object on the earth experiences the force of gravity due to the earth, and the gravity also governs the motions of celestial bodies. The gravitational force that can act as a distance without the need of any intervening medium. All the other forces that common in mechanics are contact forces. As the name suggests, a contact force on an object arises due to the contact with some other object, solid or fluid. When bodies are in contact, example a book resting on a table, a system of rigid bodies connected by rods, hinges, and the other type of supports here, where there are the multiple contact forces for each pair of bodies that satisfying the third law. The component of the normal to the surface in contact normal reaction. The component parallel surfaces is in contact to the called friction. Consider the forces that arising along the when solids are in contact uh, with the fluid. For example, for a solid immersed in a fluid, that is upward buoyant forces equation, that the weight of the fluid that displaces, and the viscous force, air resistance, etc., also called the examples of contact forces in terms of it. And where the other common forces that are in the tension and that is spring, and the forces due to the spring when the spring is compressed or extended by an external force. Restoring force is generated. This force is usually proportional to the compression of elongation for small displacement, and that the spring force F is written as F equals to minus kx, whereas kx is displacement and the k is the force of constant, and that the negative sign denotes that the force is opposite to the displacement from the unstretched state. For an extensible string, the force constant is very high. The restoring forces of string is called tension, and it is customary to use a constant tension T throughout the string, and this assumption is true for the string of negligible mass. And the way in the last chapter that we had done in the first chapter that we learned about the four fundamental forces in nature. You can go ahead if you had not visited that, you will find out there. Of these, that the weak and the strong forces appears in the domain that do not concerns us here, and only the gravitational and the electrical forces are relevant in the context of mechanics. And the different contact forces of mechanism, that the different contact forces of mechanics mentioned above, the fundamental arises from the electrical forces, and this may be seen separately. That's surprisingly basically. On the same way, we'll be considering it surprisingly, and that is the sense we are talking to the uncharged and the non-magnetic bodies in mechanics at the microscopic level. All bodies are made up of charge constituents, that is nuclei and the electrons, and the various contact forces arising due to the elasticity of body and the molecular collision and impact, etc., that can ultimately be traced by the electrical forces between the charge constituents of different bodies. The detailed microscopic origin of these forces is however complex and not useful and hanging problems in mechanics at the microscopic scale, whereas in the same way, this is why they are treated as a different type of forces with their characteristics, properties determined empirical as well. Now we'll discuss about in the detail, that is about the friction here, and of course that will go long when we discuss in the detail, because we have as well as we have your numerical on that same way. So we rest here cases so that we'll discuss the rest in the next coming class. But of course, before resting it up, because the friction is the topic that will take one itself a new class, we will discuss about it, and then after that we'll discuss your circular motions as well. But other than that, here we go for a table that has been being important one, so that we'll write it down for the quantity, the symbol, the unit, the dimensions, and the remarks as well. So we made here, so although we go for it, so in 42th class we'll start discussing about the friction. So we'll discuss the table here. The first column we will be making is your quantity. The another column is symbol. Third is units. Dimension. And the remarks. So we'll go for it. We'll discuss momentum, force, impulse, static friction, kinetic friction. So for momentum, we have symbol P. Unit is kilometer second inverse or Newton second. Dimension is mLT inverse. Remark is vector. Force, we have 4 Newton. mLT inverse square F equals to ma. Second law. For meter second inverse or ns. mLT inverse impulse equals to force into time, which is change in momentum. Fs, this is Fk, Newton itself. mLT inverse square, mLT inverse square. F is less than equals to mu Fs and F k equals to mu k n. So here we're going to end up with. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Please like, share and subscribe so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you.